Hi folks, Vipin here. Today we're going to talk about electric charges and fields. Now before I start doing the problems related to this, I'll explain a few concepts which are related to electric charges and fields. Now, let me first tell you what a charge is. Now, a charge is in fact either at the subatomic level an electron, or it could be a proton. As you all know, electrons have negative charges and protons have positive charges. Now, to be very honest, no one has really seen a proton or no one has really seen an electron. We know that they exist because of calculations and because of experiments. Okay? And by those experiments and by those calculations, we've been able to arrive at the concept of an atom. Okay? We've been able to arrive at the concept of an atom. Now, previously it was theorized that the center of an atom, the nucleus, is in fact containing a proton, and around it, in fact, you have electrons that spin about. Now, no one really could prove this because they had another logic. If you have a charge here which is positive and the electrons being negative, shouldn't the positive and negative attract each other and the whole atom in fact could collapse and disintegrate? Why doesn't this happen? We came across another discovery that in order to avoid the whole system from collapsing, you have another subatomic particle, which is the neutron. This has the negative, this has no charge whatsoever, and because it has no charge, it's able to bring balance to the atom. And this is in fact the basic of how charges and all these concepts actually originate. When you have electrons move or when you have protons move, as in case of hydrogen, that's when you have electric charges being generated. Now in most cases, any object is neutral in terms of charge. It is neutral. I say neutral because the number of protons it has versus the number of neutrons is in fact equal. So if, let's say, an object has 5 protons and 5 electrons, the charge on the object happens to be neutral. The object actually gets charged when there is a variation in any of these. Let's say there are 6 protons, the object becomes positively charged. Or in case there are 5 protons and 6 electrons, the object becomes negatively charged. And that's when the concept of ions are in fact brought in. You say a positive ion or a negative ion because in case of a positive ion there are no protons, for a negative ion there are in fact more electrons. Now, this is the basics of charge. There is a lot more which I will do in another video, but this is just to give you a background of the topics we will discuss in the problems which I will do in a few minutes. Now, because of protons and electrons, you have an electric field. That is generated. Now, we've not been able to feel an electric field by ourselves, but if you compare this to a magnetic field, it's almost the same. It's not the same, but it's almost the same. In order to understand an electric field, it's better off if you start understanding what a magnetic field is. Now, if you have 2 magnets, okay, and you try to align them together, you see that you can actually feel some sort of force when you try to bring the magnets together. Now, North and South Pole and South Pole being aligned, the magnets will obviously repel. Now, as you try to push them down, you can actually feel an invisible force that sends these magnets backwards. Now an electric field is something like that. It's an invisible force We've not been able to see it, but we know it's there, like again through experiments. Now, understanding an electric field is one of the most important concepts that is there in this particular unit. Now, firstly, remember that the strength of an electric field, and an electric field is represented through these lines. The strength of an electric field depends on the strength of the charge here. Let's say I will consider an electron here. If an electron here has a high charge, which is in fact measured through coulombs, the electric field happens to be stronger. However, if the charge here happens to be weaker, the electric field also becomes weaker. This is some of the fundamental concepts that is there in this unit, and let's move ahead with the problems related to this. Okay. Now the first problem here, consider a uniform electric field, which measures 3 into 10 to the power of 3 newtons per coulomb. What is the flux through this field through a square of 10 centimeters on a side whose plane is parallel to XY plane? Okay, a square of 10 centimeters. What is the flux through this field through a square of 10 centimeters on a side whose plane is parallel to the XY plane? So this is the first one. The second question they have is, what is the flux through the same square if normal to the plane is 60 degrees with the x-axis? Okay, if it is one case it is parallel, so it is this. In the other case it is 60 degrees. Let's assume 60 degrees is something like this. Okay, so this is first case A. What is the second case? What is the flux through the field? Flux is given by the Greek letter of phi. So what is the flux through the field when you have the charge which is parallel, and in the second case when it is 60 degrees? Now, in the first case, it's pretty easy to find, because when you have to calculate electric flux, you use this very, very simple formula. The strength of the electric field multiplied by the area on which the electric field is actually falling on. Now, there is one common mistake which students usually make. The value here has been given in centimeters. Okay. Now, centimeters is not something that you would use normally. You need to convert centimeters into meters. So 100 centimeters is equal to 1 meter. So 10 centimeters is equal to about 0.1 meters. This is something that you need to do. So 3 multiplied by 10 to the power of 3 multiplied by the area of a square. Area of a square is always given as a square. Now consider this 0.1 square, and you should get the value as 30 volt per meter. This is the SI unit to measure flux. Now before I proceed with the second category, wherein you have to consider it normal to the plane with 60 degrees on the x-axis, let me tell you a little bit about a square here. This is an old concept which the Egyptians actually brought in. Now what they would do was, they would want to measure a piece of land. Let's say you have a piece of land that is something like this. Okay, we'll consider a rectangle. Now, how do you go about measuring this piece of land? Because it's pretty big. So what they came out with the idea is, let's divide the rectangle into different squares. And let's measure this one side. We'll divide the rectangle into say 8 different squares. We'll measure just one of these squares, and the rest of it in fact becomes easier. In fact, a square is one of the easiest shapes in geometry which you can measure without any difficulty at all. all you need to do is measure just one side and everything else can be calculated afterwards. That's when they brought in the concept of a square. Okay? In order to find the area of one, all you needed to do was find the length of one side and you can calculate everything else afterwards. This is a very, very ancient concept which the Egyptians have given us. And the whole equations and everything, the background of all of them goes back to measuring land, which was initially divided into squares. The second case here wherein you need to consider 60 degrees, 60 degrees normal to the plane. So, here phi will be equal to A multiplied by cos 60 degrees. Now, this will be equal to again 3 multiplied by 10 to the power 3 multiplied by 0.1 square multiplied by 0.5. How did I get 0.5? The value of cos 60 happens to be half, it's nothing but 0.5. This should give you the answer as 15 volt per meter. So, this is one of the fundamental problems that you have in electric charges. Let's do another one, 2 more problems. Now, the second problem which we will discuss, a point charge measuring 10 millicoulomb is at a distance of 5 centimeters above a square of side 10 centimeters. What is the magnitude of the electric flux through the square? Okay, I'm sorry, this is not millicoulomb, it is in fact micro. Okay, micro is this. So, value of Q is 10C. Also remember, in some of the problems they would have given you the value of the charge as negative, say negative 10 microcoulomb or positive. Accordingly, you will have to use the formula and consider the sign as well when you use it. Okay? Now, what is the magnitude of the electric flux through the square? In this question, they've given it as, think of the square as a cube. Think of the square as a cube. Now, if you read the question carefully, it says, what is the magnitude of the flux through the square? Now, a square happens to be a two-dimensional object. It's very hard to calculate the flux through a two-dimensional object. So in order to make it simpler, you need to convert this into a three-dimensional object. Hence the hint has been given as, consider the flux through the cube. The flux in fact is going through this. Okay? This makes your calculations in fact easier. Now, when you consider the flux here, you are considering it through just one of the 6 sides of a cube, right? Only one side. I'm only going to consider this, the ones which are marked here. The rest is not something that I will consider. So this is why I will be using this particular formula. E equals Q divided by the permittivity of free space multiplied by 1 by 6. I consider 1 by 6 because I'm considering only one side of the cube. Okay? If it were to be 2 sides, it's always 2 by 6 and 3 sides and so on. Now, Q here has been given as 10 into 10 to the power of minus 6. Divide this by the permittivity of free space, 8.854, multiplied by 10 to the power of minus 12. This multiplied by 1 by 6 should give you the answer. E equals 1.88 into 10 to the power of 5 newtons per coulomb. This is a very, very simple question. All you need to know is read the question carefully and look out for those little hints that the question actually tells you. I'm not sure in the exam will they actually mention that think of the square as a cube, but the hint here is the magnitude of the electric flux through the square. Through the square is what you need to consider as the hint when you want to do this calculation. Okay? Now, we'll move on to one more problem. 3. A point charge causes an electric flux of 10 to the power of 3 newtons per coulomb to pass through a spherical Gaussian surface of 10 centimeters. If the radius is doubled, what would be the flux passing through the surface? This is the first question. If the radius were to be doubled, what would be the flux passing through the surface? The second question is, what is the value of the point charge? Okay, what is the value of the point charge? Now, if you consider the first case, that is, the radius is doubled, what is the flux through the surface? Now, let's consider one sphere here and another one here. Now, this is the first sphere. The question says, there is an electric flux here, that is, you have electric lines of force here. The electric lines of force are being caused because of a charge being present here. In the first sphere, the electric flux here happens to be -1 into 10 to the power of 3 Newton per coulomb. Now, if the radius of the sphere were to be doubled, obviously it becomes bigger. In the second sphere, what would be the flux? Now, this is actually a bit of a trick question, because if the radius of the sphere is doubled, the electric field, the intensity of the field doesn't increase. The reason I say that is because if you remember the theory that I mentioned a few minutes back, the electric field strength depends on the type of charge. The charge here is constant. The question says, if the sphere were to double, what would be the intensity of the field? The intensity, in fact, is the same. In fact, the answer here you need to write is, the electric field or the flux here doesn't change because the sphere being doubled doesn't affect it. If I say there is a charge here of, say, 1 coulomb, this is pretty big. If I have a charge here of 1 coulomb in a sphere of this size and another charge here of, say, 3 coulomb, what would be the intensity of the electric field? Obviously, this will have a greater intensity and a bigger flux because there is a bigger charge here. But if I were to keep 1 coulomb here, the flux here in both cases and the electric field in both cases would be the same. It doesn't change. The intensity of the field and the intensity of the flux can only change only if the charge here were to be different. But the charges here are constant. So there is no variation in the electric flux, nor is there a variation in the electric field. Okay? So the answer here would be the same, it doesn't change. You just need to write a lengthy sentence here saying that it doesn't change, and you need to mention why it doesn't change. The second one here they go about asking is, what is the value of the charge? The value of the charge is easy to calculate because you know the formula for electric field. So same thing here, Q here is nothing but permittivity of free space multiplied by the electric field intensity. So what does this become? Let me change the marker, it's losing ink. Here you have 8.854 multiplied by 10 to the power of minus 12 into -1 in this case. -1 becomes positive because, you know, switching LHS and RHS. 10 to the power of 3. This should give you the answer. The value of the charge is 8.854 multiplied by 10 to the power of minus 9 coulomb. So, this is how you calculate when you have this particular type of question. We will do one more problem, and with that I will close this video. Now, this question, problem number 4. A conducting sphere of radius 10 centimeters has an unknown charge. If the electric field is 20 centimeters from the center and measures 1.5 multiplied by 10 to the power of 3 newtons per coulomb, find the net charge on the sphere. Find the net charge on the sphere. Now, when you want to consider this, the data here, again I'll read it out. There is a sphere of radius 10 centimeters. Okay, from the point to the center, radius here is 10 centimeters. Okay. The electric field is 20 centimeters from the center. That is, the electric field is somewhere here. Okay. From here to here, it is 20 centimeters. 10 plus 10, so 20 centimeters. Here you have the electric field, and somewhere here you have the charge. Okay. So what you need to find here would be the net charge on the sphere. That is, how much of charge do you have all over the sphere? Okay. Now, this is an extremely easy question, but slightly tricky. So here is what you need to do. E here equals Q divided by 4 pi permittivity of free space E square. I consider D here because it's the distance from the center to the electric field. The electric field actually is going on here. Okay. So from here to here I consider the distance. If the question said the electric field is on the surface of the sphere, if the question actually said the electric field is on the surface of the sphere, my calculations would actually start from here. But it actually says the electric field is 20 centimeters away from the center. So 10 centimeters from here, another 10 centimeters here, this is where the electric field actually is going on. So I need to consider the distance from the center to the electric field. And so this is what I would be doing. Q here is unknown, but you already know the value of the electric field, which is 1.5 multiplied by 10 to the power of 3 divided by 4 pi, 3.14. Please don't take more than the 2 digits of pi. Pi is infinitely long. 3.854 multiplied by 10 to the power of minus 12. Again, I need to convert the distance into meter. So 20 centimeters is nothing but 0.2 meter. 0.2 meter multiplied by 0.2 square. This, upon calculation, gives me Q equals 6.67 multiplied by 10 to the power of minus 9 coulomb. Remember again, I consider the distance from the center till where the electric field is going on, and hence I require to use 0.2 here, that is 20 centimeters as the distance. If the question said what is the electric field in fact is happening on the surface of the sphere, I would have to consider 10, but in fact it says it's going on all the way to here, so I need to consider the distance as 20. Okay, I hope you found this video helpful. If you want me to work out more problems, let me know. Thank you for your time and have a nice day. See you guys.